Well, it's my pleasure to introduce Professor Talea Mayo, who's giving our seminar today. Talea earned a Bachelor of Science degree from Grambling State University in 2008. And then in 2010, she earned a master's, and in 2013, a PhD right here at the University of Texas in computational applied mathematics. After that, she spent 2 years as a postdoc at Princeton University working under Ning Lin. In 2015, she was appointed an assistant professor at the Department of Civil, Environmental, and Construction Engineering at the University of Central Florida. And then in 2020, she became an assistant professor in the Department of Mathematics at Emory University, where she is now. And today she's going to be telling us about her work on climate change impacts on hurricane storm surge risk. So Talea, it's all yours.
Thank you so much. It is great to be here. I'm sorry that I could not be there in person. And I was mentioning to someone that if there's one talk I would have loved to give in person, it's to UT. But in any case, here we are. So I will present to you kind of two projects that I've worked on, both answering or exploring the same research question, which is basically, as the climate change, how is storm surge risk going to change? So I'll start by giving you kind of a brief overview of hurricane storm surges for those who aren't familiar, and then discuss hydrodynamics modeling, and then the two projects that I've worked on. So one, probabilistically assessing storm surge risk, and then also using a deterministic approach. So coastal regions are interesting to me because they're the intersection of both physical processes and the built environment. So I kind of see them as a buffer where the land and environment is meeting the built environment. It's home to more than 40% of the US population, and the population is expected to increase over the coming decades. Unfortunately, coastal regions are also at an increasing risk of natural hazards. And so the two that I focus on mostly are floods, coastal flooding, and coastal erosion. And so here I've cited two papers that I wrote with my first PhD student. And so she used a lot of morphodynamics modeling to understand how we might mitigate erosion due to climate change. So the other coastal hazard that I focus on is hurricane storm surges. So hurricane storm surges are the abnormal rise of water generated by a storm. And so in this figure, you're looking at the mean sea level, and then you have like a normal high tide. Storm surge is anything above that caused by a storm. So I think simplistically, you can think of storm surge as the net result of surface wind stress pushing towards the coast or in the direction of the hurricane, and then bottom stress that's trying to hold everything in place. And so two of the papers that I've cited here kind of address each of these components. So if you want to improve storm surge modeling, then usually you can make good contributions by attacking one of these. Storm surges also pose the greatest threat to life and property from a hurricane. And just for reference, Hurricane Katrina caused maximum storm surges of about 28 feet in the Gulf Coast. And then more recently, Hurricane Ida caused surges of 8 to 10 feet, also along Louisiana coastline. And so you have seen if you're familiar with National Hurricane Center, then in recent years, they've really improved their products to explicitly depict the storm surge risk. So these are tweets that they sent during Ida or issued during Ida that are surrounding storm surge products, where we're really trying to get away from discussing hurricanes in terms of category or the maximum wind speeds, and more discussing explicitly what's the amount of coastal flooding they may cause. So this is an image from Hurricane Katrina. So after Hurricane Katrina breached the levees in New Orleans in 2005, this is more or less what New Orleans was looking like for almost 2 weeks after the storm. And this is actually the hurricane that sparked my interest in this disaster. This is an image from Hurricane Sandy, which struck the Northeast coast in 2012. And so it also had kind of catastrophic impacts. So the transportation system, the flooding, or the subway system in New York was flooded. And so there was kind of cascading effects because of that. And then lastly, this is a picture from Hurricane Harvey, which occurred in 2017, I want to say, in the Houston metropolitan region. And so Hurricane Harvey was actually more of a rainfall event, but the storm surge elevated the water levels in the Gulf of Mexico in a way that made it difficult for the runoff or rainwater to drain. So all of these are kind of unique examples of how hurricane storm surges can impact the built environment. So we can model hurricane storm surges using what are known as the shallow water equations. So here you basically have conservation of mass and conservation of momentum. They're derived from Navier-Stokes, but you depth average the equations in the vertical direction. So the shallow water equations are appropriate for coastal regions because the vertical length scales are small compared to the horizontal length scales. And that's what you need to make the assumption of constant in the vertical direction. So if you solve these numerically for H and U or Q, then your result is an estimate of what's the total height of the water column at a particular area, and then also what are the velocities or the currents at that same place. The model that I was trained on at UT is called ADCIRC, the Advanced Circulation Model. And so it discretizes the shallow water equations in space using finite element methods and in time using centered finite differences. So what that means specifically is that the finite element discretization in space allows you to have more resolution, so you can use what's called unstructured grids. So you don't have to uniformly discretize your spatial domain. You can have more resolution in a location of interest than other places, and that allows you to save on computational costs. So what you're looking at here is this is kind of the coastline of North America. So here you see like the Carolinas, this is Florida, the Gulf of Mexico is here. And so these are all little triangles that have been used to discretize the spatial domain, but the triangles are smaller near the coastline because you have more resolution there. And so this again is allowing you to get more detail and more accuracy in the places that you care about. Another model that I've used extensively is called the SLOSH model, sea, lake, and overland surges from hurricanes. So this model was originally developed in the 1960s by the National Weather Service. And it was developed to simplistically represent storm forecasts as they came in so that you could as quickly have like a forecast of what the storm surge might look like. And so it discretizes shallow water equations in both space and time using finite differences, but kind of gets away from the constraints of having a structured mesh by using polar coordinates. So the grids look something like this. And so because polar coordinates are used, then by default, you have more resolution near the poles. So this is a mesh that I use in some of the work that I'll show you later, these four. And so here you're seeing kind of more resolution near the coastline because of the polar grids. I guess I should mention that a large advantage of the SLOSH model is that it's fast. So finite differences are more simplistic numerical methods than finite element methods, which the ADCIRC model uses. And so the ADCIRC model can be more accurate. You have the ability to resolve more finely the areas that you care about, but it comes at an expense of computational costs. So a large benefit of this SLOSH model is that it produces storm surge forecasts really fast. Okay, so hydrodynamic models are used to forecast storm surges during hurricanes, and they guide emergency management and response. So this is after the fact. So using best track data, I think for Hurricane Ida. So this uses the ADCIRC model. This is the SARA website, which is hosted at LSU. It's using the ADCIRC model to say what is the storm surge going to look like for a given storm. And so this is using best track data. So it's after you've done kind of the analysis of what was going on as opposed to forecast mode, but this also works in forecast mode. So as a storm is approaching landfall, you can go to the Sierra website and look at what, based on the predictions of the hurricane, what are the predictions of the surge? And again, these come from ADCIRC. There are similar products like this for SLOSH. But the question is kind of, how do we prepare for extreme events that seem to be occurring more regularly? So essentially the idea being that if there's a storm already approaching land, it's kind of too late to do infrastructural things to mitigate your risk and your damage. So what's a better way to prepare? And so this is really a question of coastal resilience. So coastal resilience measures include nature-based structural and non-structural approaches to mitigating storm surge. So natural approaches would include things that are naturally there. So for example, wetlands just kind of naturally buffer hurricane storm surges. Nature-based measures would be implementing things that, or let's call them green infrastructures that will mitigate storm surge. So you might install dunes that should also mitigate surge as a storm approaches. And then you have structural measures, which are more traditional, like gray infrastructures, like levees or seawalls. And then finally, you have some non-structural approaches. And so I'll take this opportunity to ask you, what do you think is a non-structural approach? Is one of the ones I found the most interesting when I first started studying this problem. Okay, so essentially, if you're trying to improve the resilience of a coastline, what's a non-structural approach you could take? And Jita says managed retreats, and that's a great example of a non-structural approach. So you could think of like mandated retreat or incentivized retreat. So basically asking people not to build in areas of high risk, so then you don't have as dire consequences when an event does happen. I think another good example of a non-structural approach would be like insurance rates. So if your insurance rates are so high that people don't want to build there, then you're basically encouraging people to move away. What about renters? Can you ask your question differently? Renters who don't have insurance, then maybe would get like an incentive, could be a non-structural approach. So maybe some financial incentive to move. And maybe we'll talk more about this in the discussion. So in order to really have true coastal resilience, then you need long-term planning and risk assessment. So if we're going to implement, for example, nature-based solutions or green infrastructure, then you need to have some idea of what you're building for. And so this is where the hydrodynamic modeling will come in. Okay, so here in this first body of work, then we conducted risk analysis to really inform strategies for coastal resilience. And so let me just give you some background information. So this is an example of like a histogram of maximum storm surges. So this is one way that you can quantify risk. So here you're looking at number of events on kind of this y-axis and then level of storm surge on this x-axis. And so you can consider this like a histogram of a large number of storms. So for risk assessment, for particularly coastal flood risk assessment, what we actually care about is the tail of this distribution. So we're really concerned about the low frequency, high impact events. And so that's kind of, I would say, not typical, right? We're used to wondering about means and modes, so maybe down here, but when we're talking about preparing for worst case scenarios, then we're really interested in the tail, the ones that have the high impacts. Okay, so what we do in this work is model this tail using a generalized Pareto distribution, as called. So there's kind of a number of distributions you could choose, but basically you're trying to model this tail as opposed to making assumptions about the full thing. It's the tail that we care about. And so there are other methods, peaks over threshold methods, where basically you're choosing a threshold, or what is the level of surge that you're concerned about or that you want to explore. That's defined as U or mu. And then you'll compute the probability that it's exceeded. And then you can fit the data that you have out there in this tail using what are called scale and shape parameters. So basically going to fit what's the behavior out here. And then once you have the fit of this distribution, you can use those same parameters to develop what's called a return curve. And yeah, I'm always used to talking to interdisciplinary audiences. So maybe you're familiar, but if you're not, then let me get you familiar. So the return curve is basically just going to describe a measure of probability. So if we look out to, for example, here, the 100-year flood level, then we can find on this corresponding y-axis that it's about 3.5 according to this curve. So you'll hear people discuss like the 100-year flood. If you know the return curve, then you're able to discuss what's the 100-year flood, what's the 500-year flood, et cetera, just based on this curve. So what exactly is it? It's a measure of probability that a specific return level or specific height of flooding is exceeded annually. So for example, the 100-year storm surge has a 1 out of 100 chance of exceedant each year. And so I always like to emphasize the each year part. So you could expect to have 200-year floods in a single year, because the 100-year level is just describing the probability annually. And so I think what I'm trying to clarify is that it sounds like the 100-year flood is something that happens once in 100 years, but really it's just the denominator of the annual chance of exceedance. Okay, so the 500-year storm surge or 500-year flood would have 1 out of 500 chance of exceedance each year. And so I wrote a paper for the notices of the AMS, the American Mathematical Society, that just describes just this. Okay, so again, we're concerned with low frequency, high impact events. And if we have the data, then we can model these events using a generalized Pareto distribution, and then get the return curve that we'll use to that will kind of center our design and resilience efforts around. But the problem is that by definition, we're concerned with the low frequency events. So probably we don't have this sort of data to come up with these curves. So if you think about like how often does a hurricane happen, and then if we're talking about risk in a specific place, how often does it happen in one specific place, then you probably don't have this kind of data to develop these methods. Okay. And then even if you did have enough data for a particular place, then we know that the climate is changing. And so historical data by itself is insufficient to really understand what may happen in the future. Okay, so our approach to address this issue was to use synthetic hurricanes. So we collaborated with an atmospheric scientist who developed synthetic storms that can represent various climate scenarios based on climate model data. So the atmospheric scientists will develop 2,000 to 3,000 for this work, synthetic storms for any given climate scenario. And then if we're thinking about a specific location, then we specify that the storms that are modeled should come within 2,000 kilometers of a site, and they should be at least tropical storm strength so that we know we're probably getting things that will be in that tail that we're interested in modeling. The climate scenarios that we looked at for this work include the NCEP-NCAR reanalysis. So that's like data that's representative of the current climate or early 21st century climate. And then also end of century climate data. So we use the RCP 8.5 emission scenario. That's the no intervention kind of worst case scenario from the IPC, the fifth annual assessment report of IPCC. And then we used 4 climate models, and then these 4 were chosen out of the suite because they represented kind of the range of possibilities. So these emissions, this specific emission scenario, worst case scenario, was used with global climate models, and then that data was downscaled to produce 2,000 to 3,000 synthetic storms. So in the end, we have 2,000 to 3,000 synthetic storms that represent each climate scenario that we are interested in. Okay, so the storm data, here I'm just showing the distributions of the storm data. So you have the NCEP data, so that's this black dashed curve. And so that's supposed to be more or less the truth. That's what we're observing. That's what's being simulated to represent the truth. So the storms are still synthetic, but they're using observed data, generated using observed data. And then all the other dashed lines are the modeled data. So they're coming from climate data, but climate models that are representing the current climate or early 21st century climate. And then the same models are used with climate conditions simulating the end of 21st century climate data. So basically what you're looking at is dashed lines are the models or observed representation of what's going on now, and then the solid lines represent how that's going to shift by the end of the century. On the left, I'm showing the maximum wind speed, so that's intensity. And then on the right, I'm showing radius of maximum wind speed, which is one measure of size. And so there's kind of variability in what we're seeing on the size, but definitely for the maximum wind speed, for example, if you look at the GFDL curve, the blue curves, you're seeing kind of this peak down near 50. And then for the end of century, you're seeing this shift to the right. So basically the intensities are becoming stronger. And that's pretty characteristic of each of the global climate models. And then of course, you're also seeing that there's not like a solid agreement, right? There's variation in what is being produced based on the climate data that's being used. For radius of maximum wind speed, again, the results are not quite as conclusive, but I would say you do also see kind of these shifts. So these solid curves have higher modes over here for the larger maximum wind speed. So basically the sizes you could generalize and say are also increasing by the end of the century. So once we have this synthetic storm data, we also know that sea level rise will impact our level of flooding. Okay, and so we have local sea level rise estimates as well. We approximate their distributions and then basically convolve the distributions of sea level rise with the distribution of surge to understand kind of what is the shift in the distribution for total flood. So for our study, we looked at 4 sites. And so here I'm just going to show you results for Jamaica Bay, New York. So Jamaica Bay, New York is at the bottom of Long Island. And so I'll show you results for this location, but we also did the same exact experiments for these other 3 sites. So Narragansett Bay, Rhode Island, Atlantic City, New Jersey, and then Norfolk, Virginia. And so we chose, I didn't, but our collaborators chose these sites because they were identified as one, susceptible to inundation, so high risk for the coastal flood hazard, but then also socioeconomically vulnerable. So maybe more in need of informed information about their future flood risk. So here you're seeing the return curve for Jamaica Bay, New York in the present day, which I just called 1990 climate data. So this is the return curve that we get when we use synthetic storms generated from basically observed data. And so based on this curve, then we're seeing the 100-year flood is 3.3 meters. And so what we really want to do is understand how does that number change by the end of the century. So if we convolve the distribution that we get for the end of century flood data with the projected sea level rise for the mid 21st century, then you get this green curve. And so what you're seeing is really the curve shifting to the left, and the 100-year flood becomes the 57-year flood. And so if you're remembering, this is just the denominator of annual probability of exceedance, then more or less your probability of this flood level, 3.3, is doubling by the end of the century. If you convolve the distribution with the end of century sea level rise, then you have an even greater shift. And so the 100-year flood becomes the 29-year flood. And so I'm also listing kind of what's the vertical change. So if we just look at the 100-year flood, how is that increasing? But I think I like to focus on kind of this horizontal shift because people tend to build around the 100-year flood or the 500-year flood, right? So in this case, if you're building a structure around the present day 100-year flood, then by the end of the century, your structure is insufficient, right? Because it's not the 100-year flood anymore, it's the 29-year flood. But here we're really only considering the sea level rise contribution. And so what we're stating from this work is that we also know the storms themselves are changing. So we want to understand how does our flood risk do, or how does flood risk change if we also consider this? So we'll use the modeled climate data to understand this. And so first we'll develop a return curve based on global climate model data for the present day climate conditions. And so that's what this dashed line is for GFDL model. And so again, you notice that it doesn't exactly align with the return curve that we got from the observed data or the INCEP data. But since we're using the same model, then at least we can observe what are the changes. So there is variability in kind of what each model produces as the present day return curve, and that's just due to the uncertainties within the models. Okay. But what we see is if we convolve kind of the mid-century data with the mid-century projections of sea level rise, we see shifts, and we see even greater shifts than we saw if we don't consider changing storm climatology. So here, when we looked at just the NCEP data, so only assuming sea level rise, we saw the 100-year surge become the 57-year surge. And if we also consider changing storm climatology, so how does this dashed line change to this green line, then the 100-year surge is becoming the 34-year surge, right? So there's an even greater increase in the annual probability. And then of course, if we look at end of century sea level rise projections and end of century projections for changes in tropical cyclones, then we get an even greater shift. So we said that the 100-year surge would become the 29-year surge by the end of the century if we considered sea level rise. But here, if we also considered changing storm climatology, we see the 100-year surge become the 6-year surge. So even if you try to account for sea level rise, if you don't also account for the changing storm climatology, you still underestimate the risk. And then here's kind of just a visual in various return curves. So here in the previous slides, I was discussing the 100-year flood level for Jamaica Bay, New York. So now we can see similar trends in other flood levels. Okay, so what you're seeing in this slide is for the 50-year flood, the 100, the 500, and the 1,000-year flood, you're seeing this decrease. So that from the leftmost point to the center point is if you account for sea level rise, how does the return period change? And then on the far right, then you're seeing if you also integrate the storm climatology, right? And so everything has this negative slope, which means the return level that starts at 100 or 1,000 or 500 or 50 is decreasing when we account for these climate change factors. One thing you can again see is kind of the variation across the model. So there's definitely work to be done in resolving some of these uncertainties that come from the global climate models. Also, I'll say that it seems like for the MRI model, there's not much of a change when we consider this changing storm climatology. And so for the data that we use, this was the only model that predicted decreases in frequency. Right, so the frequency, even if the storms intensify, if their frequency decreases, then you see that reflected in the changes in risk. Okay, so we produced similar work for all 4 of the sites as part of this large interdisciplinary project called Structures of Coastal Resilience. So the landscape architects that we worked with published a book in 2018 that really discusses more holistically kind of like all of the aspects of increasing coastal resilience. And then we also just had a paper accepted that really focuses just on the methodology for estimating the flood risk. So probabilistic modeling is great, it's exciting, it's fun, but it depends on these synthetic storms that are generated from a statistical model. Okay, and also the computational cost is prohibitive. So I mentioned earlier that one of the main benefits of the SLOSH model was because the numerical methods that it uses are simplified in a way that makes the model much faster, and that was why we use that model for this work. But SLOSH is also not quite as accurate, or you cannot resolve it as well as you can, for example, the ADCIRC model. So we wanted to also use a better model to get a picture of changing flood risk. Okay, and so for that, we really need deterministic approaches. So we did a deterministic approach to assessing climate change impacts to flood risk. In 2020, this paper was published in 2020 in Weather and Climate Extremes with my second PhD student. Okay. So the WRF model, it's the Weather Research and Forecasting Model. It's a 3D convection permitting regional climate model. It has 4 kilometers of horizontal grid spacing and then also a vertical element. So it's a very high resolution regional climate model. This model was used to simulate hurricanes after a climate change signal was imposed on the boundary conditions, just to understand kind of what would be the effects of climate change on hurricanes that had already happened. And so actually 22 hurricanes that occurred from 2000 to 2013 were simulated under present day climate conditions using WRF. And then again, with the end of century climate change signal imposed on the boundary. And that work was published in 2018 by my collaborator, Ethan Gutman, and his collaborators. So what we did as this part of the work was understanding, well, since we have these hurricanes, we can see how do they change over the century? What does that mean for the storm surge? Okay, and so since we're doing basically deterministic modeling, we can use a more expensive model, and so we use ADCIRC. What's really interesting about the specific configuration of ADCIRC that we use is that we use this mesh, which is pretty highly resolved. So it has 1.8 million vertices, which means that's the number of places that we're calculating H and Q, or the height of the water column and the currents. And it has overland grid resolution ranging from 150 to 500 meters. So this is a map of kind of the bathymetry of the configuration we use. And so the green you're seeing is inland. And so this mesh is different from a lot of standard ADCIRC meshes because it goes on land. So we're able to really assess what's going on over the coast or beyond the coastline. And so here's just one example of the types of simulations we did. So for all of the 21 hurricanes that we simulated the present day hurricane and then the end of century hurricane. So it's the same storm, just one has a climate change signal imposed on the boundaries. And so this IKE gives us a really nice illustration of kind of the changes. And so since our mesh goes overland, then we're able to calculate metrics related to inundation. So we calculated inundation volume, or how much volume is overland by the end of the simulation, and then inundation extent, so what area is covered. And so really from this slide, the takeaway is that things are increasing, right? So the inundation volume went from 23 cubic kilometers in the present day climate to 30 cubic kilometers at the end of century climate, right? So it's a lot more flooding that you would have to deal with. And same with inundation extent. So there's the numbers, and then you can also see visually just how much more land is being covered. Here is kind of a composite map where we're subtracting the present day flood from the end of century flood. So a positive number means end of century flooding is greater. And then the negative number means that the present day flooding is greater. And so overwhelmingly for the cases that we looked at, you see this red. So there's a few places where things are blue, and we attribute those to like minor track changes. And there's some storms that just kind of de-intensify as they were modeled. But the majority of the storms will cause more surge at the end of the century than present day. And then here's the like a table of all of the storms that we modeled. So here's the storm, and they're ordered in terms of the inundation volume from greatest to least. So how much water did they cause? And then once we impose this climate change signal, so pseudo global warming case, then what's the new volume of inundation? And then we looked at percent change and whatnot. So there's a few negatives again, but for the most part, or on average, then you're seeing that the level of inundation, the volume of inundation is increasing. Then another thing we tried to kind of tease out was, well, why? So here things are ordered in terms of the change in volume, right? So we're going from blue to red on this last column. And so what we're looking for is some correlation between storm parameters that we know affect storm surge. So for example, wind speed is, we want to know what category storm is approaching land. Tends to have some relationship to how much surge can be expected. So we would expect as the volume is increasing, maybe the wind speeds are also increasing, or vice versa, I guess. As the wind speeds increase, then the volume should increase. Basically, we don't see that, and we don't see that for any of the other parameters either. And then specifically, we can see cases where basically all of the storm parameters intensify in the ways we know them. So wind speed is greater by the end of century, the radius is larger, the translation speed is slower, and the pressure is lower. So everything's worse by the end of the century, but then the volume is not worse, it's less. And then Dennis is an example where we see the opposite, where everything is de-intensifying, but we still see more volume. And so a lot of that we think, again, is due to slight changes in track. So even if a storm de-intensifies, if it hits a different area that's maybe at lower elevation, then you would expect more surge. But there's more work to be done in really understanding this question. We really have used it as motivation for the need for deterministic modeling. So especially as kind of there's this desire to introduce machine learning into things, this is a really difficult application for that. And then we separated our present day data and end of century data to see like, well, maybe the changes aren't exactly related, but are the parameters related to storm surge volume at all? So here for present day, the volume is the one that we're ordering in terms of. So these storms are listed in terms of their increasing volume inundation. And then again, we're looking for some pattern in the storm properties. So wind speed, radius, translation speed, and pressure. And again, we're just not seeing a really clear gradient in present day data or end of century data. Yeah, and I guess specifically we were concerned about wind speed since that's the one that kind of the general public focuses on a lot. And so we can see here that the storm surge risk is not directly related to storm intensity or maximum wind speed. So we have another paper about the kind of lasting impacts of the Saffir-Simpson scale, so category 1, 2, 3, 4, 5, on people's perception of risk, even though we know and we see in our own work that it's not correlated. So just to conclude, I will say that storm surge is a low probability but high impact hazard. How low probability is greatly impacted by tropical cyclone frequency, which is uncertain. So we saw when we modeled with the global climate models, we used the storms from the global climate models that predicted lower frequencies that really affected kind of how the probabilities changed over the century. But how high of an impact is impacted by a lot of things, which includes kind of the typical geophysical characteristics we think about. So tropical cyclone intensity, size, translation speed, and their uncertainties. And then also other things that are part of the system that define risk. So in Katrina, the impact was exacerbated by a levee failure or a failure in infrastructure. For Sandy, I think population density and kind of the transportation system had a lot to do with the impacts there. And then for Harvey, the compound flood event or the effect of the rain and the surge combined, and then also the infrastructure because a lot of the natural mitigation was removed to build this metropolitan area. And that affected how chaotic the results of the storm were as well. So computational mathematics and numerical storm surge modeling is an essential tool for risk assessment. And then I like to end with multidisciplinary research is really critical to addressing coastal resilience in the truest sense. So that is the end of my talk, and I would love to take any questions you have.
Thank you very much, Talea. When we open the floor for questions, either from the seminar room or from the Zoom. If you're on Zoom, go ahead and raise your hand, and I'll call on you. Otherwise, in the seminar room, I think yeah, I see the blue cube. Okay,
yeah, we've got a question.
Okay, all right,
and
we'll get you next, Gita.
Yeah, I feel like we should have priority if we came to the room.
You get the cookies.
Exactly. That was an awesome talk. Thank you so much. I had a question about you showed us a slide that had the change in the return interval for like the 50 year, the 100 year, the 500 year.
Okay, with the diagonal.
Yeah. So one of the things that's striking to me about this, and I'm curious about your thoughts, is that the higher intensity, bigger events that are less frequent have steeper slopes there, which would mean that their return periods are changing more, I think, than the gentler events. And so okay. I would think, like, from a long-term perspective, in terms of impact, that's a little bit scary. And I'm kind of curious, how robust is that? And do you have thoughts on that? Is that it seems like that's a pattern that shows up in the return curves themselves as well, right? That the 1,000 year becomes more like 100 year, whereas the 100 year only increases in frequency by, say, 3-fold instead of 10-fold.
Right. Yeah. So I think one thing that I will acknowledge right away is just the further out that you're predicting, then the more uncertainty you have. Yeah. So like here, right, we're really talking about stuff that's way out here where we may not even have a lot of data points to produce these curves. So I think first we should acknowledge the uncertainty there. And so I did some work like trying to get good estimates of uncertainty for the higher levels, but that is apparently its whole other research questions. So I don't really know what to say except, I mean, it's not good news. Like, we're certainly trying to better understand the extremes. And so yeah, I mean, I think this agrees with the literature that's out, which is that even if the frequency doesn't change very much, it's like the high intensity storms are what we can expect more of. And yeah, I don't have a lot of thoughts besides like I tried to kind of detach from what it actually means and might look like in 100 years. Do you have more thoughts?
I think that's no.
Okay. I mean, I appreciate the recognition, and I don't know, I don't have a lot of good news.
Gita, why don't you go ahead?
Sure, and I actually did have a thought on that, which you brought up at the very end, that this idea in the climate projections is that the overall number of hurricanes decreases, but the maximum intensity ones become more frequent and more intense. And so I would be interesting to know how much that signal is driving this behavior that you're seeing in these curves, because it would produce this outcome where your lower intensity events don't increase by as much, but your high intensity events really increase. So that would be interesting to see. But then the question that I had was a little bit related to the point you made about Harvey at the end. And I was curious, how do the models that you're using consider the compound effects of flooding from sort of land-based extreme precipitation when they're mapping out areas of maximum flood risk? So can you see where the storm surge may interact with locations of maximum runoff based on topography, or is that sort of beyond the bounds of what you can simulate here?
Yeah, so this is like a really active research area right now, compound flood assessment, basically. So for the models that I use, they're too coarse to really resolve rainfall runoff. So people will do things like impose a boundary condition from like a river to try to like represent this. But it's definitely an active area, and largely because the scales are so different, I think is what makes it such a difficult problem. But there's definitely active work. I think, in my opinion, you need like a sophisticated coupling between two. And I mean, yeah, I've not seen anyone simulating like rain, but more like runoff from it. And so there's hydrology models that I'm not as familiar with that people use, and I've seen used. But I would say, yeah, this is an active research area and not something I think you can do especially well with just ADCIRC.
Yeah, thanks. That's really fascinating. I wonder if there's like some just first order adder that you could include that brings into account the fact that we think you're going to get more precipitation with these landfalling cyclones, and they're going to be slower moving. So we expect more extreme flooding from precipitation. And so it would be interesting just to be able to know what the percent contribution from that would be compared to the storm surge or something.
Yeah, like what would the impacts be on the flood? Yeah.
And go ahead, Duncan.
Yeah, really interesting talk. Yeah, you touched on some things that get communicated to the general public. The hurricane scale that you see on the Weather Channel and the return curve, and you mentioned that there can be some confusion with them. Has there been any work on trying to come up with an alternate lexicon for, you know, making sure the Weather Channel uses something more, maybe more responsible in terms of communicating risk?
Yeah, so the paper that I reference is this one. And basically, like, our conclusion is in the title, that there just needs to be more social science research surrounding, like, how do we really compensate for this, like, deep-seated idea of the correlation. We looked more at products from NOAA and National Weather Service than we did, like, Weather Channel. I think in some initial drafts, we did have some examples pulled from Weather Channel, but I don't know what they're actively doing. I think we just like decided to narrow to what were NHC, National Hurricane Center, doing in their products, because they kind of affect the decision makers more, and then I think the decision makers then affect the public. So it's not something we explored, and I'm not sure. I definitely have seen, just in my own experience. So I was living in Florida during Hurricane Irma. and then, so that was like a big storm with a lot of like media frenzy. And I definitely have noticed like an emphasis on the surge that might be caused. So I've seen like local weather newscasters, like the one in specific particular that I follow, like from Alabama, was like my favorite during that storm, because he just did a really good job of like clearly stating what were the impacts. So I think the information's out there. It's just kind of like, I think the information conveyed to the public is also conflated with like, how am I going to grab people's attention? So it's hard to say, like, are they prioritizing this? But I've seen it, like I think there's promise.
Thank you.
Hey, Sean, go for it.
Yeah, a great talk. I guess my question is, how do we, or whether it's already starting to happen, where there's a better linkage between risk assessment at more of a local level and these kind of assessments of different type of storm tracks and effects of ideas of how they might mitigate. So for instance, do we have a case where someone can talk about a wetland restoration project and then have some models that can leverage and say, this would be the positive effect on storm surge if we made these changes, or are we not there yet?
Yeah, so I think in short, I would say, I don't think we're quite there yet. And that's largely just due to my like interactions with public policy people, urban planners, have just more or less told me like the state of the art is not being integrated the way that it should be. I think at a high level, like we're talking about it, but I think when it comes down to kind of dollars, it's not being integrated the way that we would like to see. And I think it's easy to do because this is like, we're talking in the future, right? So it's easy to ignore it for the sake of kind of what's going on right now. So I would say maybe there's some improvements, but inadequate, I would
So
say.
as a follow-up, what would you recommend then an important next step be?
Yeah, so I'm working with this group in Georgia that spent a lot of time in Savannah, connecting with, communities. And I need to like iron out the details of how did they initialize the engagement. But I think that's the best thing. So basically, instead of trying to do like this top down, if we can do more bottom up and really get to the people, get people understanding, then I think like by effect, then it has to start to come out in the policy because people want to see it. So I think the most fundamental thing to do is like public education.
Hey, any more questions, either from the peanut gallery or the Zoom callers? If not, let's thank Talea again. It was a wonderful talk, and I'll see you in a few minutes. I'll get the meeting Zoom going again, and okay. I saw Damien going up to his office, so he'll join that as well. So
okay, and I think for the people in the room, since I can't like see the names, if you want to send an email with follow-up or schedule something, then please let me know.
Thank you.